Hello everybody, this is Dr. Keith Schubert. So we're continuing our state implementation. This is where we left off on the last video. You can see we made our Carnot maps for our state bits, our least significant state bit. The little n, if you recall, means next. So this is our next state bit 0 and next state bit 1. So 2-bit state. The state graph that we are implementing here is shown in this graph and this table. But we'll at the moment just take a look at the particular implementation here. Now, once we have these equations, we have one set of equations. Remember, we had some options. We could either do this, which uses ands and ors, or if we noticed, we could do this one, which uses an XOR for the same bit. So we have an option. They implement the same exact thing. For the second bit, there wasn't a nice XOR gate or something like that fits. So I decided to just go with the basic 3 encirclements of the ones pattern. So that gives us this. So we're going to want to implement this. Now, I know some people have had problems installing things, so I want to introduce you to an online tool that I really like. I'll put a link to this inside of on the page this is on, so you can get here, and you'll be able to. The link will take you and give you actually all of my code, so you can play with it. So might be worthwhile pausing the video at this point and going to this link, and then once you've got the code pulled up, you can follow along on your own and kind of watch the video as well. So take a sec here and do that. Just pause me and pull that up. So hopefully at this point you now have everything pulled up. EDA Playground is an awesome tool. You can do a lot of designs. It's kind of broken up. There's a left window and a right window. You can for code here. The left window is used for test benches and other types of setups. The right window is used for your design. You can upload designs and everything else. Logins are free, so you're allowed to share things. So this is code from my login, but if you're going to run things and modify things and save it, you'll have to make your own login. It's really easy to do. So I would suggest making a login so you could save things and play around with it. That'll enable your save and your run. If you attempt to do it without, it should actually tell you, hey, you need to save this and give you a link. So it's very user-friendly in that sense. So these two are where your code go. This is the log and other information that you see. So when you compile and run it, it'll give you all your information here. On the left-hand side, it gives you your options. So for the test bench and design, I've picked System Verilog. You'll notice that there's a lot of different options that are in here. VHDL, and then some special ones, right? SpecMan E, right? So there's a lot of options for how do you glue stuff together. Python, along with System Verilog. You can describe your whole descriptions in Python or C++ System C, which is an alternative to Verilog and VHDL that basically are extensions to the C programming language. Perl can do pretty much anything, and C shell. So these are all different ways you can run your code that's on there. We are not using UVM or OVM in later courses if you are interested in going further. So these are the universal verification methodology. Verification validation is a really important area, and we do cover it in later courses, so we kind of build up to it. I will talk about one thing that's a little bit more advanced than the basics that you will need inside your lab, because I think it's just a good intro and it's fun and easy, which will be this random command down here. Just show you different ways you can kind of get interesting random input. You could, of course, use a known sequence that's on, but for a lot of testing, we actually do kind of want this random. Anyway, so there's, this would be more advanced stuff, so we're not going to worry about that at the moment. Um, if there's any other libraries you need to run this, we don't. Um, they give you some compiler options. We don't need them. Um, they ask you to select a tool. Of the tools they have available, I like this LDEC Riviera Pro. It's a really good compiler. There's a bunch of really good ones. Synopsys and Cadence both have very good ones. Synopsys actually has a lot of cool features on it. Um, Icarus Verilog is an open source one. It runs on any platform. So if you want to get your own version, it will run on Mac, it'll run on PC, and things of that sort. The disadvantage is it doesn't implement all of Verilog. It won't do the random. So there are a lot of things it's not able to do because they're kind of aiming for an older version of the language. I think it was like 2000, up to maybe 2001, 2005, something like that. For some reason, 2005 sticking in my head as their goal language. And they've really just been working constantly on trying to get that one fully there. So I'm not as particularly big of a fan of it. The Verawell is also a pretty good compiler, but they also have all your standard C++ and all that kinds of stuff. But this LDEC Riviera Pro is a really good compiler. I like it a lot. It has a lot of nice features. It'll take you all the way through, so it's a good one to kind of get used to, at least on here. So compile and run options, I just did standard ones. These are your timescale units. So, I just gave them standard version, and this is telling it to use System Verilog 2009. Um, basic access stuff. How long does it run for? And the only thing I've added is open this EP wave. So EP wave files, as a default, if you don't set this, and then there's some dump vars, we'll talk about this in a sec. If you don't set it up, you won't see the waveforms at the end. So you have to check this open EP wave. That's the wave file that stores what it all looks like so it can be graphed. And this generates the wave file so it's available for running. So this will allow us to do it. Also, as by the way, EDA Playground has lots of good examples, and Doulos is a great source for both Verilog and VHDL code. I like a lot of what they do. They're one of the better sources of information that's out there. I warned you that there's unfortunately a lot of people who write old code and not necessarily the most documentable and extensible ones. So you want to be careful not to learn bad programming habits. And Doulos does a really top-notch job. Anyway, so that gives you a quick overview kind of the interface area. I'm going to walk through the test bench because my personal opinion is you should design a test bench to the original design model that's here. And as a kind of your first overview, one set of stuff, you want to make sure, independent of the design, you test that the functionality you want is here. The second thing you'll do is take particulars about here that could be problems and add those tests in. So those are two stuff. Since we're kind of early on, I'm going to mainly concentrate on a generic one because it will allow you to test. We'll do this in several different formats. So that will kind of be our goal. So we're going to want to build and design this around the idea of implementing these different, a test to do this state graph. So we'll kind of walk through this. So the module, I call this Model1. So this is Model1 test. We're going to have for our models, and I have the same inputs. I've actually got several different ways that I could build it, a gate level and using equation behavioral type modeling, register transfer level or RTL model. So I have several different models, but I made them have the exact same interface. That allows me to switch between them by just changing this model one, and then I put whatever the level is after it. So I can just switch it here, and since I'm using the same interface for all of them, essentially that's the only thing I have to change is these few letters here, and I can test any one of these model versions. So each one of them there's an input, clock, and reset that comes in, and the output is going to be my overall state queue. Notice I do this as a wire. This is deliberate. I'll show you why inside the design. Um, but it will return a state queue to me. Therefore, I have to declare what's going to be on the test bench side to go into this device under test. Um, so everything that's going to be an input, I have to have as a register so I can change it inside an initial, or an always, but I might use initials because they're test benches. So I have input, which initially is a 0, clock, which just starts high, and reset, which starts high. And then the state, which is a wire, it's 2 bits, 1 to 0, and I call it Q. Under here, I just pass everything to everything. I think this is kind of a cleaner way of doing it. You could put this final parentheses and semicolon outside. Um, I like the read of it this way, but suit yourself on that last one. I don't really care. But this gives you kind of your basic design input. And then I made different initials for different types of things. So this first one sets up my clock. So I essentially tell, if you remember, clock started out as a 1. So what I'm going to tell it is every 5 nanosecond clock becomes not clock. So that means it takes a total of 10 nanoseconds for the clock to complete one cycle. So this kind of sets it up, and I'm going to set up 1,000 of these clocks. There's several different ways you could do it, but this one kind of lets somebody know, oh, it's just a faked clock using an initial. I set this 1,000, so it's more than big enough to cover everything I want. You could take and calculate what time period you want here. I'm not worried about for a beginning one, but this first one is really just totally there to build the clock. The second one that comes in, this just sets up all of my waveform stuff. So it does what's called a dump file. Whenever you see a $sign, that means it's a command to the interpreter that's kind of running things in the background and handling it. So it's not technically a Verilog command. It's actually for the Verilog compiler and simulator telling it to do something. In this case, the first one is specifying where do we output the data for each of the different signals that we're reading. So this is a data dump. So therefore it's called a dump file. And I just give it a file name, model_1 VCD. You can pick whatever you want. As long as it's a .vcd, that will hold your Verilog data for you. And then I say dump vars, and I just give it a blank. So if you say blank, it means dump everything. But you can also specify things. So the basic format for specifying things is a number and then a list of variables. The variables are modules. So one kind of tells the level, or the number tells the level of stuff. Typically people will pick like 1, which 1 or even 0, which essentially it's going to pick either the particular module or the module and everything below it. And then you can list what the modules are. So I could say Model1 test or something of that sort. But I personally just like to dump everything because you never know what you're going to need. If you're too specific, it can get kind of tight. If you have a really big design, you probably don't want to dump everything because it just becomes big and slow and wastes a lot of space, particularly if there's stuff you don't need. But my experience in the past has been if I needed something, invariably it wasn't done, and then I got to deal with this whole pain in the rear thing trying to get it all out. So as long as you're not space constrained, and at least as a first guess, I would just dump everything. And then if you discover that it's too big on any particular design, then you can downscope it. So anyway, this just sets up the file at the end. There are other commands that you can tell it to, stop the dump and resume the dump, and You can change the variables partway through, but then realize you're only going to be able to plot portions at different times. Um, yeah. So anyway, but you can look them up. There's a whole bunch of $dump commands that are out there. These are the only ones I really care that you know. Um, then this next loop does the resets. So it at the beginning point, so from 0 to 5, reset is high. And we'll see in a sec, we're going to do resets when it goes low. So I do an initial reset that clears things, make sure all the variables are set up right. And then 5 nanoseconds later, I set it back high again, and I do nothing else with it. So it just does this initial, clear out the memory state so that I'm starting at a nice beginning state for my variable of all the internals are 0. All right, so now everything's kind of set up. The last one here is going to do the actual data that I care about. So I wait 5 nanoseconds on the input, and then I set it to be equal to a random variable. Percent is modulo 2. So I just say, take this random, and calculate basically a thing. So it's 0 or 1 is basically what it's going to end up generating. So this gives me randomly that the input is either a 0 or a 1. Random also has parameters. You can set the seed. If you don't set the seed, it picks a default 1, but the default one that it picks is deterministic. So therefore, every time you run it, you'll get the same thing. But, or at least the same sequence, but it will flip around in a way that's kind of hard to predict, other than if you happen to memorize the number sequence. But I kind of like that because I don't then have to make some long sequence of things. So I do this initial wait 5, and then 20 times I wait 10 nanoseconds. That's my cycle time. This first half of 1, make sure that the data is stable, or my input is stable, for 5 nanoseconds before the clock receives its positive edge, which is when it does a data read. And then this one waits for the next, it actually changes input on the negative edge. So this is negative edge, and these are all subsequent negative edges. So we do the changes on those so that it's stable around the positive edge when it's going to be doing the read. Let's see. So that takes care of the kind of randomization part of it here. So 5 nanoseconds random, and then 20 times it'll do 10. It waits 10 more nanoseconds after the last update, just so you get to see what happens after the last update. No more updates are coming, so then I just tell $sign finish, which means stop the simulation, and that will essentially finish everything out and get me my plot. So that's the idea of the test bench. And my whole goal here, remember, other than, the reset coming in, which just clears things out, and the clock, which lets things move regularly, the input's the one that really drives the state changes. And this allows me to just do a random one. So this is a very nice, fast, easy way to do them. Last time I checked, the older versions of Vivado do not support random. It is possible the latest one. They kept promising they're going to add them. I haven't looked at the latest version to see if it has. I've heard they were supposed to. I've been skeptical because they've been telling me that for a while. But honestly, I got too much going on right now, so I'm not going to check this probably till summer. But if you want to, you could try it on Vivado. Eventually, they will support it. This is a very old requirement inside of the Verilog compilers commands. So Verilog does specify a set of these compiler commands, dump vars, and all that. So it is part of the language, even though it's not a technical Verilog command. It's a compiler one, and it just says, hey, make a random number and stick it in here for me. All right. So that gets us all of our test bench. And that'll be the same test bench we test everything on. Now we've got 3 different designs. I'm going to go through and do the gate level one that comes in. So we'll take a look first off at this right here. That's what we'll pick up. I'm gonna actually stop the video at this point, and we'll do each of the designs after, because we've kind of gone through the interface of the test bench and of the general EDA playground, and that'll allow me to do short videos on each of the individual models with their simulations. So I will stop here, and this video won't get too long, and then you could pick up with the other ones in whatever order makes you happy. But I'm going to do it gates and then equations and RTL.